Today you are witnessing a colossal industrial sawmill built to process giant sequoia logs of an
This is a giant sequoia, nearly 1,000 years old. Its sheer size forces the factory to rely.
Every truck enters the exact lane and position. A deviation of just a few centimeters is enough to block the entire processing line behind it. Even the act of releasing the restraints follows strict safety protocol. The log is so heavy that any uncontrolled shift is unacceptable. We place the log onto a roller bed to begin washing and debarking before scanning the internal core.
The surface must be completely clean. Any remaining debris would distort the scan results and rapidly dull the cutting blades during the sawing process. Debarking exposes the structural wood beneath. Bark and wood residue are collected separately, never allowed to mix with load-bearing beams.
From this point forward, each giant sequoia log is managed as an engineered structural component, no longer treated as raw wood. These identification codes allow full traceability, from internal core scan results and cutting paths through drying and treatment. The wood record is created the moment the log enters the facility. One incorrect parameter is enough to disrupt the entire production line.
Before any cutting begins, we must know what lie inside: hidden cracks, internal voids, or structural weaknesses. Ultrasonic scanning reveals the internal structure. Any zone with a risk of cracking is excluded from the primary load-bearing beams.
X-ray inspection forms the second layer of verification, detecting dead knots and internal voids that ultrasonic scanning may miss.
Not every part of the log is suitable for load-bearing beams. We classify each section according to its structural grade. This is the moment the factory decides how to cut, maximizing beam length, thickness, and structural safety. Marking directly on the log ensures the saws follow the calculated map with absolute precision.
And this is the heart of the factory, the large block sawing zone.
The clamps must lock completely. Even the slightest vibration would ruin a cut weighing several tons. Large format bandsaws are used to break the sequoia trunk into primary beam slabs.
The blade must be cooled and cleaned continuously. The wood density is extreme, and the cutting width is far beyond standard scale.
Every cut creates a structural surface. From here, we begin shaping the future beams.
Incremental feeding allows precise control of slab thickness, keeping dimensional deviation to an absolute minimum.
These slabs will be cut further into thick beams designed for load-bearing bridge structures. Beam thickness between 200 and 400 millimeters forms the foundation for heavy load-bearing structures. Immediate sorting after sawing prevents any mixing of quality grades further down the line. End trimming removes crack-prone sections and brings each beam to its exact design length. Structural beams are not allowed to exceed curvature limits. Any bend will cause alignment errors during bridge assembly.
Proper stacking allows air to flow evenly, preventing moisture buildup and structural deformation.
Rough beams must be surface stabilized before entering deep drying. Now comes the most critical stage: drying structural timber. Timber used for bridges must reach a controlled moisture level, typically between 12 and 18%.
Convective airflow removes moisture in a controlled way, preventing thermal shock to the wood.
We don't measure a single point. We measure the entire batch, because every beam behaves differently. Dry too fast and the wood will crack. Dry too slow and it will miss specification. Everything must follow the correct curve. After drying, the wood is not used immediately. It must first be allowed to equalize. Equalization stabilizes beam dimensions before precision processing begins. Every beam must carry a verified moisture certificate. Without certification, it does not move forward. Even with proper drying, small cracks can still form. The task is to detect them early and address them immediately. We remove every weak point, preserving only the strongest wood for load-bearing beams. Once moisture is stabilized, the beams are finally ready for outdoor protection. Because bridges stand outdoors, wooden beams must be protected from the inside out. First, a vacuum is applied to draw air out of the wood fibers. Then the protective solution is pumped in, and pressure is increased, forcing it deep into the wood. The goal is long outdoor service life, continuous exposure to rain and sun, while remaining structurally stable. Excess solution is recovered. The beam retains only what has penetrated the wood structure. Surface drying prepares the beams for precision machining, dry, stable, and free from surface moisture. From this point forward, every structural beam meets the requirements for outdoor environments. And now comes the most industrial phase, precision machining of load-bearing beams. Four-sided planing brings each beam to its final dimensions and creates stable, uniform contact surfaces. Incorrect dimensions lead to incorrect bridge assembly. That is why measurement immediately after planing is mandatory.
CNC machining creates connection grooves and bearing surfaces with the precision of industrial modular assembly.
Bolt holes are force transfer points. One misplaced hole compromises the entire structure. Primary beams and secondary beams must be clearly distinguished, so nothing is assembled incorrectly on site. Bridge decks are not just about appearance. They must drain water effectively. No pooling, no slipping.
We assemble everything here in the factory, so on site it becomes a matter of placing each piece in its exact position.
Load-bearing beams must be straight and stable. Torsion is not acceptable. The surface is prepared so protective coatings can bond properly and enhance long-term outdoor durability. The UV protective coating is the final armor before exposure to sun and rain. Proper curing of the coating ensures a durable surface and stable color over time.
At this point, we have a complete bridge kit, fully prepared inside the factory.
Before leaving the factory, primary beams must pass simulated load testing. We do not measure by feel, we measure by data. Only when results remain within allowable limits is a beam granted factory certification. Proper packaging ensures beams are not damaged and do no regain moisture during transportation.
And with that, the bridge kit leaves the factory. From the sawmill, we carry the structure to the site where the real bridge will rise.
The site is ready. This is where giant sequoia beams will be assembled into a bridge made entirely of wood.
The primary wooden beam is lifted first. This is the load-bearing backbone, made entirely from solid giant sequoia.
Every bearing point is wood. Wood beams rest on wooden supports, transferring load directly through laminated timber structures. The second wooden beam locks the entire span using mortise joints and load-bearing wooden dowels, forming a fully timber load-bearing frame.
Secondary wooden beams distribute loads evenly into the primary beams, allowing the entire timber structure to work as one unified system. The entire bridge surface is wood. Thick timber decking with active drainage is designed for long-term outdoor use. The railing is also entirely wood, providing safety while increasing the overall stiffness of the bridge deck. There is no load-bearing steel. All load testing is performed directly on the giant sequoia timber structure.
The final protective layer prepares the wooden bridge to face rain, sun, and time itself.
From a 1,000-year-old giant sequoia entering an industrial sawmill, through core scanning, beam cutting, drying,